Okay, so as you all know, security proofs of quantum cryptography rely on assumptions, and some assumptions are quite natural, like the validity of quantum mechanics, for instance, but other assumptions may be more questionable, and it is often the case that real-life implementations of quantum cryptography do not conform to the theoretical models which are used to prove their security, and this may open security loopholes. And so this problem has led people to introduce new protocols where security can be proven with reduced set of assumptions or without having to trust completely the quantum devices. And there are different ways to come up with such protocol, but one nice approach is to start from the correlation that you can observe in simple scenarios involving black box devices. So one example is device-level protocols, which are based on these schemes used to demonstrate non-locality, where you have two measurement devices, which you don't need to trust, so you can view them as black boxes. And the only thing that you need to believe is that these two boxes do not communicate during certain runs of the protocol. Another example is provided by semi-device-level protocols, which are based on a prepare and measure scenario. So we have a preparation box that sends some states, which are measured by a measurement device. And again, you don't need to trust them, so you can view them as black boxes, except for one assumption, which is a qubit assumption, which says that the states sent by the box here must span a two-dimensional Hilbert space. And these protocols are called semi-device independent because actually to verify that this qubit assumption is satisfied, in practice, you would need some partial characterization of the devices. But in both cases, the idea is the same, is that if the underlying assumption is satisfied, and if you observe certain correlations between these two devices, then you can draw interesting conclusions about how the devices behave. And we just saw an example in the previous talk by Valerio, where he explained to you how if you observe the violation of an inequality, you can conclude that a certain entangled state is shared between the two devices. And these inferences that you can do, that you can make about the implementation based on the correlation can then be used to prove that a certain protocol is secure or that the implementation is correct. So what we did in our paper is that we introduced a new kind of black box scenario of this type based on a new assumption. So why consider a new assumption? Well, device-level protocols are very nice, but they're very hard to implement. They require these fancy loophole freebell tests. Semi-device-level protocols based on qubit assumption are much easier to implement, but this qubit assumption is poorly justified. So as you know, carriers of quantum information, like photons, they have many degrees of freedom, so they naturally live in an infinite Hilbert space and require that all the states exactly span a two-dimensional Hilbert space. This is something that is artificial. So for instance, this is the scheme that was used to demonstrate experimentally a random number generator based on a qubit assumption. And this was presented at QCrypt 2 years ago. And actually, if you go through the detail of the scheme, which I will not go into, you can convince yourself that actually the qubit assumption is not satisfying this implementation and will actually never be satisfying unless you have perfect ideal components. So this is an example where we have a mismatch between the theoretical model and the implementation. And this example illustrates an important point, which is that the aim of device-independent or semi-device-independent approaches is not to base security on a reduced set of assumptions just for the sake of having few assumptions. The really important question is, does the theoretical model match with the implementation regardless of how many assumptions you have? So this is the important thing to consider, and this was not the case here. So what we did in our paper is we consider a prepare and measure scenario. So you have a preparation device which sends states. So you have also preparation choice x. So for any preparation choice you made, there is a state rho x that's output here, and this state is measured by some box, and you get some output B. And again, you can view these boxes as, I mean, they do not need to be trusted. They're black boxes, except for one assumption, which you can formulate as follows. So imagine that this box is outputting quantum optical systems, which can be arbitrary multimode systems. Then the assumption is that all the states emitted by the box are close to the vacuum. So the overlap with the vacuum is large. It's bounded from below by some parameter, omega, which you're free to choose. So depending on your implementation, you choose adequately this parameter, but it should be close to 1. So saying that the states are close to the vacuum, well, this assumption will in particular be satisfied if the optical signals have an average photon number which is slow, or if the energy is slow. This is why we call this an energy constraint. So why do we like this assumption? Well, we like it because it has a physical meaning. It represents a physical property of the systems which are emitted by the box. As such, it can also directly be related to simple characteristics of the components inside your device, like the power of a laser, the absorption coefficient of an attenuator. And also because this energy constraint represents a physical property, it can maybe also be directly monitored, maybe using a calibrated power meter. And so this should be contrasted to a qubit assumption, which is more artificial. For instance, if I show you this experiment, and I tell you there is a qubit in there, do you trust me? But if I tell you this light beam has a very low intensity, does that sound more reasonable? And another reason why we have taken this assumption is that assumptions about photon number statistics are anyway implicitly made in many quantum optics experiments, which often use attenuated covariant states. So we say, why not make it explicit? OK, so what can we do in this setting? So if you believe that this underlying assumption is satisfied, and you observe certain correlation between the two devices, what can you conclude? So we look at this in the simplest possible setting, where there are only two preparation choices on this box, so x equal 1 or 2, and the measurement device is implementing a single measurement, which has binary outcomes, so b is equal to plus or minus 1. Now, you would observe correlation between the output b here and the choice x if, let's say, when you make the choice x equal 1, b is biased toward plus 1, and when you make the choice x equal 2, b is biased towards minus 1, or the other way around. So the correlation between the two boxes can be quantified by the quantity E1 and E2, where Ex is just the average value of the output bit B, given that I've chosen the preparation choice X. Okay, so this quantity X is just the trace of rho X times M, where rho X is the unknown state sent by the box, the preparation box, and M is the unknown measurement implemented by this measurement device. And more generally, if the two boxes can share arbitrary Schur randomness, you would write this like that. OK, so now assume that in an experiment I observe some value of E1 and E2, and assume that the only thing I know is that the average overlap with the vacuum is above some threshold. What can I conclude? Well, assume that the vacuum is represented by this state, which is pointing in a minus z direction. So since I know that the states emitted by the source are close to the vacuum, they should also point towards this minus z direction, right? And suppose I observe some strong correlations between the output B and the choice X. So this means that from the output of this measurement device, I can to some extent distinguish what was the preparation choice, right? So what's the best way to distinguish two states which are which are pointing close to this minus z direction? Well, obviously, I would like the two states to have the smallest possible overlap, which means that one should be on the right side of this axis and the other on the left-hand side. And the best measurement then that will discriminate them will be a measurement in the x direction, which is a basis which is almost complementary to the preparation basis. Okay? So in summary here, if I make this assumption about the energy of my states, and if I observe strong correlation to the device, I can conclude that the source sends states in some basis, and the measurement made upon them was made in a complementary basis. Okay? But this, of course, then will imply that the output of a measurement device must contain some randomness. It cannot perfectly be guessed by an adversary, even if he has a very precise description of the devices. And actually, we can quantify exactly how much random is the output. And this is possible because for any value of this parameter omega, we have exactly characterized the set of correlations which are compatible with quantum mechanics. So this set is represented here for a certain value of omega. So this is this blue or purple region. And we have an analytical characterization of this set for any omega, and also an SDP characterization. And because we now understand what are all possible ways by which these two devices can behave according to quantum mechanics, if this assumption is satisfied, we can also understand how much randomness is produced when you observe certain correlations. And this pink region here will correspond to the deterministic regions. So these are correlations which are such that they can be produced by devices which behave completely deterministically, so that an adversary could have perfect knowledge of the output. So anything outside of that pink region corresponds to a realization where you can certify that some randomness has been produced. And so this picture actually is completely analogous to what you would have in a standard non-locality scenario, where this hyperplane here, separating the deterministic region from the genuine quantum region, would correspond to a band inequality. And so because of this similarity with non-locality, we can use tools and IDs which have been developed for device-independent random number generation protocol and adapt them to a scenario. So you can specify a semi-device independent random number generation protocol based on this setting, and you could analyze its security using tools which have been developed for analyzing the security of certain device-independent random number generation protocols. Okay, so I told you that we can certify randomness in this setting, and we can build random number generation protocols around it. But how do we implement such protocols? So how can I get some point here which is outside this deterministic region? What kind of states should I prepare, and what kind of measurement should I do? There are different possibilities, but one simple implementation is just to have a source which prepare displaced vacuum states. So in phase space, you prepare one state which is displaced toward the plus x direction, and the other towards the minus x direction. And then the measurement that you do is just a measurement of the quadrature of your field, and the output you assign is the sign of the quadrature. So if I prepare this state, B will be biased toward positive value. If I prepare this state, B will be biased toward negative value. So this is something that's quite easy to implement. You can also even do it with integrated optics. And this energy assumption on which you base the analysis, I mean, this value of this parameter omega, you should set it depending on how much you displace the state from the vacuum. Okay, so if you implement something like that, typically you get a point here which will lie outside this deterministic region, and just from which you will be able to certify that some randomness has been produced. If you're willing to make a slightly stronger assumption, you can also come up with simpler implementation. So for assume that the average photon number is bounded. So what this means is that in certain rounds, the states can be emitted with a very high photon number, but on average, it is low. But it's also natural to assume that the peak photon number is bounded. So this means that the photon number from one round to the other can fluctuate, but I assume it can never go above a certain threshold. And you can also make all the analysis by doing this assumption, which is a little bit more constraining than this one. And this is quite natural if you have a partial characterization, at least, of the devices. But if you do that, then you can come up with much simpler implementations. So what you need is a source which either produces the vacuum state or a weak coherent state. So basically what you have is a laser followed by an attenuator, and then you either switch on or off the laser. And the measurement you do is just a photo detection, so you either register a click or not. And of course, when you send the vacuum, you expect to have no click. When you send a weakly coherent state, you expect to see some click. So you get, again, correlation between these two devices. And if you do that, you would get a value for E1 and E2, which will fall in that region. So it's inside the deterministic set if I make the average energy assumption, but it's outside the deterministic set if I analyze things according to this stronger peak energy constraint. And where does randomness physically come from here? Well, of course, it comes from the fact that if I send a weak coherent state, then whether I get the click or not will be random. But the nice thing here is that you can certify and precisely quantify the randomness based only on one assumption, which is that the state emitted by the source are close to the vacuum. So in particular, you can treat this detector as a complete black box. So you don't need to trust it at all. You don't need to know its efficiency, the dark contrast, or daytime, anything. So you have a very strong statement about the randomness which is produced, which I think is theoretically appealing. And at the same time, you have a very simple implementation, which only involves a laser, an attenuator, and a detector, which is probably one of the simplest kind of setup you can use to generate a random number. OK, so in summary, we propose to use a bound on the energy of optical signals as a fundamental assumption on which to prove the security of prepare and measure quantum cryptography protocols, with no other assumption on the device. And we have already shown that this approach can be used to design a semi-device-oriented random number generation protocol. So open questions. The analysis of the random number generation protocol that we made assumed that the devices do not have some memory. And this memory could be used, for instance, to preload the devices with some entanglement. Assuming that the device do not have some quantum memory is something I think which is quite natural if you have some at least partial trust in the device. But anyway, I think we don't need this assumption. So it would be nice to understand how to relax it. And besides random number generation, we think that this approach can also be promising for other protocols. And we hope it can be used to prove the security of a QKD protocol. And in particular, because this energy constraint is compatible with infinite dimensional Hilbert space, we hope it could be used to prove the security of a continuous variable QKD protocol for which there are no natural device-dependent or semi-device-dependent formulations at the moment. Okay, so thank you.